Welcome back to CS520. In this session, I'm going to talk about threads. And to do that, we need to go back to the basic computer hardware diagram that I started the course with. Right, very simple model of computer architecture. Just a CPU connected by a bus to the memory. And we need to think back on what a CPU provides for us. Again, it provides it executes a fetch execute cycle repeatedly, so it's executing instructions for us. It has some internal places to store data called registers, and modern machines, in order to facilitate function calls, they use a stack in memory. So I like to think of that as being what the CPU gives us. And where are we headed? Well, we're headed to this model where we have multiple CPUs. Right, modern machines now, even our laptops, typically are multi-core, meaning they have a set of CPUs available to them, all dangling off the bus, all using a common memory. And one way to think about threads is that a thread provides a virtual CPU, right? It executes instructions. It has registers that are its own copy, not shared with another thread. And it uses a stack in order to do function calls. So this notion of a thread is really an abstraction because it lets us think of it at the software level as being a virtual CPU. It's useful for a couple reasons, at least. Useful for performance because it allows us, when we write our software, to actually exploit this multiple CPU facility that's available in modern hardware. And we can exploit that for performance, right? We can be doing instructions, streams of instructions at the same time. So we can divide a task up into pieces, and we can have threads executing those pieces at the same time if we have actual physical processors, physical CPUs available to us to execute the threads. So useful for performance, we can maybe get things done faster. But threads can be useful even if you only have one CPU, because it can be a design strategy for your software. For instance, you might assign a thread to wait for GUI events while having another thread actually computing away, doing the main computation of the application. It can be just a convenient way to structure your software. Rather than having to have the main computation thread periodically peek and look to see if a GUI event has happened, you can just assign a thread to wait for those GUI events. Okay. So that's sort of the plus side. What's the downside? The downside is that the memory is shared. Again, going back to my diagram, right, we've got CPUs all hitting memory here. Remember, von Neumann machines were fetching data as well as instructions from memory. Remember the von Neumann bottleneck that we have to go through memory to get everything. So now we have multiple CPUs that are all competing for access to memory. So memory is shared. Threads need to contend for it. That might actually have performance issues if we have to wait a lot to get to memory. And there's also correctness issues. Threads can interfere with each other in memory. We could be touching the same spots at memory at the same time, and that can cause trouble. And let me try to explain that. Consider two threads incrementing the same variable. So we have two programs. They're executing an I++. Each of them is executing I++ on a shared variable which is initialized to 0. The question is, what's the value of I after these two threads do their I++? Well, we need to consider this, knowing a little bit more about what goes on underneath the hood of the computer. What is I++ really? Well, in an abstract assembly language, we know it's load a value from memory into the CPU, probably put it in a register, and then add the constant 1 to that register, and then store the value back to memory. So the I++, you know, the word we say is it's not atomic. You know, even though we can write it in one statement at the level of C, we know the compiler is going to translate it into a set of statements. And the I++ itself is not atomic. It doesn't happen in one step, rather it happens in 3 steps. And that's problematic, as we'll see. Because we need to consider interleavings of those low-level instructions. You know, what the threads are really doing then is this sequence. And here's one possible interleaving where T0 is running a little bit ahead. So it does load I first. And then concurrently at the same time, if we think about time going down the slide, at the same time that T0 is adding 1 to its copy of I, which again, remember, is inside the CPU, probably in a register, T1 starts the load. So it loads I, again, from memory. Right, if we try to start to track what's going on here, right, this one loads I, it gets the value 0, right? This one loads I, it's going to get the value 0. Okay. The next time step, thread 0 does the store. It's now storing 1 into memory, the location that's implementing the variable I. And at a later time step, this one is also storing 1. So we end up with I at the end of this, I being 1, which seems counterintuitive, right? We do 2 increments, but we lose one of them. This is sort of the prototypical problem we have with multi-threaded programming. This particular situation we call a race condition. You can think of it as it's a race. Who's going to do the store back to memory first? It's really whoever does it last that wins, right? This value of 1 is the value that ends up in I because it's done last. Right? Race condition is really one definition, one way to think about it is it's a possibility of incorrect results due to the timing of how the stream of instructions get executed relative to each other. And what you really need to think about is to interleave those instructions in various ways and consider what happens. You know, for the program to be correct, all possible interleavings have to lead to the right answer. So how do we handle this? This is why threaded programming is challenging. So we have these kind of interactions. We have multiple things going on at the same time, and we have to worry about how the threads are going to interact and consider those kind of interleavings. So we need a mechanism. In this case, we need a mechanism to ensure that only one thread at a time is in the critical section. Again, we would call that update to a shared variable, that I++, a critical section. We've got to make sure that only one thread at a time executes it. We don't want to allow any interleavings. We want one thread to do the I++ to completion before another thread starts it. So threaded computation libraries have some notion of locking usually. So if we consider adding an operation to lock, where it's like, lock is only one thread can own the lock at a time. So another thread that wants to lock the same lock would have to wait for the first thread to unlock it. It's that kind of operation. We look at now what happens with the threads. Thread 0, again, it gets a head start, does the lock first. Let's assume it's going to get the lock because nobody else owns it yet. Then it does the load I, the add 1, the store I, and the unlock. And now this stuff, the stuff in the middle here appears to be atomic because of the introduction of the lock. Notice what happens to thread 1. Thread 1 comes along a little bit later and tries to do a lock. It can't get the lock, so it gets blocked is the terminology we say. It has to wait. It's blocked waiting for the lock. So it just stalls out here, waits until the unlock happens, and now it gets the lock, and it could do the load I, the add one, and the store I. And again, that makes this I++ also atomic. So again, if we take a look closer, what happens to this? This is loading 0. This is storing 1. Come down here now. This is loading 1 and ends up storing 2. So we get the expected value, right? We get the two updates. They both get noticed. They both get counted, so to speak, and we end up with a value I equals 2. Because the lock ensures that only one program at a time is doing this update of a shared location. So that's one thing we need. We need this locking mechanism, but we also need some mechanism to control the interaction of threads in other scenarios. For example, consider a thread producing a series of values to be consumed by another thread. What kind of interaction do we want to have here? Well, the consumer thread can't consume until the producer produces a value, right? I can't consume a value until it's available. And the reverse is the case. Producer thread can't produce until the last value is consumed, right? I'm assuming a buffer between the producer and the consumer of length 1. In other words, I can only store one value. Let's assume that. Okay, so I can't produce another value until the last value is consumed. So how can I control that? Well, we need some way to have processors wait for an event to happen. With the lock, we're just waiting until we could get the lock. But now we need to wait until some event happens, like the production of a value or the consumption of a value. So let's take a look at how that might be solved. Again, I can consider a scenario like this, where I'm going to have code for the producer, code for the consumer. The shared data is some kind of Boolean that tells me whether there's actually a value present in the one element buffer. And then the one element buffer, I'll initialize that Boolean to be false, saying there's nothing present initially when we start up. And then I'll include a lock. So I need something, it turns out programs often have multiple locks, so we'll consider a lock to be a piece of data. Sometimes you hear locks called mutexes it's a shortening of the phrase mutual exclusion, which is the purpose of the lock. We want to have just one thread at a time own the lock. And then a mechanism we're going to introduce to allow people to wait for conditions is typically called a condition variable. Okay, so that's also going to be something an object that we can operate on. I'll try to illustrate what a condition variable does for us through the example. So let's look at the producer. Again, the rule is the producer cannot produce until the last value has been consumed. In other words, as long as there's a value present, I can't produce another one. So what we're going to do, as you usually do anytime you have access to shared data, you're going to first lock to make sure you have exclusive access to the shared data. And of course, at the end of the sequence, we'll have to do an unlock. So once I get the lock, and I know I'm the only one looking at the data right now, I can check the control Boolean to see if there's a value present. If there's a value present, then I have to wait. And the wait primitive operates on both the condition variable and an associated mutex. And the wait primitive requires us to own that lock, the caller to own that lock. But I'm waiting now for an event to happen. The way I'll be awakened is by a signal to this condition variable. So at some point that signal will come, it'll wake me up. I'll come in, I will drop my new value that I want to drop off into the shared location called value. I'll set the flag to say there is a value present. And then I will signal, because this is, the consumer now might be waiting. I need to tell them that I just put a value that's ready to be consumed. So this signal would wake up a waiting consumer. And then I unlock to provide access to allow the consumer to get into the data. Okay. Let's go through the other side and then we'll match them up. The other side, again, I'm going to grab the lock to provide me safe access to the shared data. I'm going to do the reverse. If the value is not present, I need to wait for one to show up. When I wake up from the wait, then I can pick up the value. I can pick up the shared value, put it in my local variable called new value that I'm going to process. I can reset the Boolean to be false because now I've consumed it, and I can signal to let the producer know that there's a value, there's an open slot that they can produce another value, and then I unlock. So let's draw some arrows between here. I mean, this signal is communicating to that wait, and this signal is communicating to that wait. Okay. This note at the bottom, it points out the subtlety of these operations. When a wait is called, the associated lock is released. So when I call wait, the associated lock or mutex is released automatically as part of the call to wait. And it's an error if you don't own that lock. When a signal is called, again, a signal goes to a condition variable that has an associated mutex, and the first waiter is going to be released who's waiting for that signal. In this case, I only have 2 threads, but in general, you can have n threads and you can have more than one waiter. So the first waiter is released. There's no guarantee, by the way, about timing or anything who's going to be the first waiter. So maybe I shouldn't say first. A single waiter is going to be released when you call signal. Maybe I should just correct that. A single waiter is released. But the subtlety is this last statement here. The newly released waiter must wait to reacquire the lock. So when you call wait, for instance here, you release the mutex as part of waiting. That allows the producer to get in and access the shared data and update the value so that you can be signaled and continue. Notice you sort of logically you need that to happen, and it happens automatically as part of the wait call. The waiter then waits until this signal comes. That wakes them up, but they first have to get the lock back. So this is something to keep in mind, that you might have to wait twice. You wait for the signal, then you wait to get the lock back. Notice there is a gap here between the signal and the unlock. So the signal will come in, you wait for that, then you have to wait for the unlock to happen. And there might be other threads out there trying to get the lock at the same time, again in a more complicated situation where you have more than 2 threads. And the important thing to realize is that you may not automatically get the mutex right after the signal. Some other thread could get in the cracks. So in fact, when we look at more complicated scenarios later, we have more than 2 threads. Usually you don't want an if here, you want a while here. Because between the time you're signaled and the time you reacquire the lock, some other thread may have come in and changed the state of the data from what it was set by the signaler to a state that you can no longer handle. You may have to wait again. It turns out you don't need it in this case with only 1 thread, 1 producer and 1 consumer. But if you think about having multiple producers and multiple consumers, you will find you need to have a while there. Okay, so that shows you a few more tools that threaded programs use to control the interaction of the threads. We've talked about locks, and now we have wait and signal on condition variables. Okay. So bad things can happen. We already looked at the problem of uncontrolled, unsynchronized access to shared data and a race condition. But other things can happen too. When you have bugs in your program, you might, if you don't do the waits and the signals correctly, you can end up with what's called deadlock, which means all threads are blocked. Everyone's waiting on somebody else to do something, but we're all waiting. So nobody's able to do anything, and the program just, it looks like an infinite loop, but it's not. It's just nobody's doing anything. Everyone is deadlocked is what we use. Another bad thing that can happen to you is you can have live lock. That the threads spend so much time coordinating with each other, responding to each other's actions, that they cannot make any progress on their own work, their individual work. So nothing is getting done. You're just synchronizing and going back and forth, and nobody's doing any work. That's called live lock. And then a fourth bad thing is called starvation, that some threads might dominate access to a shared resource. So they're always accessing the shared resource, and some other threads never get access to it. And so again, if the program is counting on all threads being able to do some of the work, it could be that the program never actually gets done because threads are being starved. They can't get access to the data they need to complete their tasks. Okay, so that's a very quick introduction to threaded computation, some of the problems, some of the solutions, sort of a generic sense. In the next lecture, we'll take a look at how these ideas are actually implemented in POSIX threads, which can be used to do threaded programming in C.